Hello guys, so welcome back to our common emitter discussion. This is basically another example uh, on common emitter amplifiers. This time we're gonna solve this circuit in DC and AC. We're gonna do everything. Okay, the previous two examples was just to explore the main characteristics of the common emitter amplifier. So we didn't care much about the DC. We assume that the DC is good. The DC is we are working in the active region, the middle of the active region, and everything is perfect in DC. Now we're gonna see this with numbers, okay? And we're gonna also learn another two tricks also for common emitter amplifiers. The first one is basically another type of biasing, which is very famous, which is the voltage divider biasing here. So in the previous two examples, this resistance was not there, R2, okay? So now we have this resistance, which makes the biasing, voltage divider biasing. Also, we have also this new capacitor here, okay? And this capacitor is really, is really a nice trick because, so we see that with degenerate resistance, we could improve, we could increase our input, we could, also make the DC Q point, stable. But how about if you want to keep the, the amplification big, okay, or large, or eliminate the, the effect of RE on the gain, but at the same time you want the DC Q point to be stable. At that time we need RE to be only in DC, and we don't want to include it in EC. And we can do that using this capacitor in here. This is called the bypassing capacitor. Because in DC, this will be open, and in EC, it will be short, so it will short out RE. So the circuit will go back to our, our first circuit that we solved it for the common emitter amplifier with no RE. The emitter will be connected directly to the ground. Okay, so that's basically the trick here in that circuit. So let's remove our mess, and try to solve it. So basically, the basic requirement here is to find AC, AV naught, AV, GV are input or output. But of course, we should solve this first to get IC or IB to determine R by and find, then find the AC equivalent circuit and get all the characteristics that you want. So starting with DC analysis. In DC analysis, all capacitors are open. Okay. And we cancel all AC, sources. We cancel all AC sources. This guy will be shorted. All the capacitors are open. This guy is open. This guy is open. This guy is open. So basically, the circuit will be reduced to the following. Which is, exactly the voltage divider circuit we solved it before. Okay. That's why, we started by the DC analysis, or we find the Q point and the stuff when we started studying the transistor circuits. So what we do here, we get the Thevenin equivalent. Of course, there are many solutions, 3 solutions as we studied before. But maybe the easiest is to get the Thevenin equivalent. So we're gonna get the Thevenin equivalent of that part, the voltage divider part in here. Okay, so this will be converted to the following. R Thevenin sorry, this is RE, not R7. And this is R7. Okay, so we know how to do that. So basically, we're gonna reduce this. Sorry, this voltage divider with R1, R2. Here is the 2 points. Let's call them A and B. I'm gonna reduce that to V7 and R7 between A and B. That's what we're gonna do now. Okay. So we did this many times before. So just review the videos before. So we know that R7 will be R1 parallel with R2. So it's gonna be equal to 9.64 kilo ohms. And we know that V7 will be basically the voltage across R2 here, assuming A and B are open circuit. So this will be VCC R2 over R1 plus R2. So it's gonna be 5.35 volt. That's nice. Now we determined R7 and V7, and then we can determine, the DCQ point. So IB. So let's start first by KVL here. So at loop 1 here, so you have V7 equal to IB RB, and we're gonna assume here is 0.7 VBE. Just we are refreshing now, what we studied maybe 2 weeks ago. Plus IERA, and we know that IE is beta plus 1, IBRA. So now IB is equal to V7 minus 0.7 over RB plus beta plus 1 RE. So this will be equal to 0.01847 milliamperes. Now let's get IC. I will not, multiply IB directly with IC. I will just multiply this with beta, IC is equal to beta IB. So I just multiply 100 by this number and I get it. But I want to show you something. So let's write this in that way. Beta, then same expression for IB, V7 minus 0.7 over RB plus beta plus 1 RE. It's easy, But before we continue, let's compare this IC with the IC that we get if there is no RE. Remember, guys, we added this degenerate resistance claiming that we will have a stable AC and a stable DCQ point, right? Right. We see how it can affect the AC and make it stable in the previous, videos. But now it's time to see how it makes the Q point stable. Let's compare this to the original RE and IB if we don't have RE. If we don't have RE, that means, you have a short circuit like this. RE is 0, right? We can put RE is 0 in the expressions. So let's do that. So the original expression of IB with no RE, if RE is equal to 0, will be something like this, V7 minus 0.7 over RB. That's it. So from that, IC will be V7 minus 0.7 over RB and beta in front of all of that. So look at this. Compare this term with this term, which is more stable or which is, sensitive to beta. Here, if beta changes, for example, doubled, IC will be doubled. It's assumed, of course, it will not be doubled. I mean, when the room warm up or something, beta will change, but not, of course, not doubled. But this is just to show you how far it can go. It can go anywhere. Whatever beta changes with some percentage, IC will change with the same percentage. Doubling, tripling, and so on. Okay, But here, beta is in the numerator and also beta plus 1 in the denominator. So if it changes, increases, for example, in the numerator, it will also change in the numerator. So they will balance each other. That's why this is more stable. You know, or we can say less sensitive to beta changes. Than this one. Than this expression if there is no RE. Okay, that's why we put, or why RE is beneficial, you know, in DC and AC. But of course, in this example here, it will not be beneficial in AC, because in AC, CE will be short circuit, so RE will go away. Because if you have two resistance, one is 0 short circuit, parallel with another resistance, whatever the value of this resistance, the equivalent will be 0. Okay, so let's continue. We get now IC, we get IB, we can get VC, you know, to be sure that we are really working in the active region. So VC is equal to VCC minus ICRC. Just looking at, you know, this is really easy. So here is VC here, VCC minus ICRC. So VC is equal to 7.796. Okay, and that's really good. Q point. This is good. Let's write this in another color. This is good. Q point. Why? We said that to get maximum swing in our, you know, when we just started, you know, exploring the applications of transistor, we said that it's good to have the Q point in the middle of the active region. So because for the maximum swing, VC should be equal to VCC over 2, which is, VCC here is 15, by the way. It's not written, but it's 15. So 15 over 2 is equal to 7.5. Here we 7.7, that's, you know, that's fine. Okay. And we can even get VB to be sure that we are working in the active region. So VB is equal to 0.7 plus IERE, or beta plus 1 IBRE. So that will be equal to 5.17. Since VB is less than VC, we are, you know, VBC junction is reverse. So we are really, you know, working in the active region, just for check. Okay, that's basically, you know, the DC part. Now the AC part, number 2. For the AC part, let's do it AC analysis. Number 1, capacitors short. Number 2, DC sources cancelled. Okay, let's draw the circuit after doing that. So we're gonna have VCC as a ground. Then the transistors in R. Then RE here we have the capacitor shorted. This capacitor here, CE will be shorted in parallel with RE. Then we have R1, R2, R signal, and V signal. And of course, since you have here a resistor in parallel with short, with 0, then the overall will be 0. So let's do it in another color to show you guys that this was basically something, you know, or equivalent of another thing. RE parallel with 0 ohm. Okay. Then we draw the equivalent circuit of the transistor. R by beta IB capacitor, I'm sorry, collector, base, emitter. The emitter now is connected to ground, which makes your life very easy. Then you have, of course, there was here RL as well. Then you have RC parallel with RL. And here is VO. Then you have here R1 parallel with R2. So you will have between the base and the ground, you have three branches. This branch R1, this branch R2, this branch R signal, V signal. So R1 and R2 will be parallel. So I'll just combine them in the combination form or the parallelization form. Then R signal, then V signal. Good. Now we can determine anything. Number one, R input. Before anything, this part of the circuit is isolated from that part. Why? Because they are connected with one point. One point. So when we get our input, which is between the terminal of the input, the signal, and here are the terminal. So the voltage, the input signal is V signal and R signal together. The internal resistance R signal. So you just see these two resistors in parallel. So our input here basically equal to R1 parallel R2 parallel with R pi. Okay. We forgot to determine R pi. So R pi is VT over IB. We know both. So R pi was 1.35 kilo ohms. We know R1, we know R2. It's a given. So this combination will give us basically, let's check this, 1.18 kilo ohms. Look, it's even less than R pi. That's what I'm saying. When we have some resistors in parallel, the resultant, the overall resistance will be smaller than the smallest. Smaller than the smallest, which is R pi. That's good. That's bad for common emitter amplifier because our input is small. Number two, RO. RO is the resistor that is seen by the load. So we look between these two, points. And of course, we cancel any source. So we should cancel. Let's do it, separately, not to confuse you. So we're gonna look between the terminals of RL. We're gonna remove RL and put Vx and Rx. We have RC, beta IB, R pi, R1 parallel R2, then R signal, then nothing, because we're gonna short V signal. And again, if we make Kirchhoff in here, so RO is Vx over Ix. Before that, we're gonna do Kirchhoff just to prove that IB will be 0 because we canceled its source. So IB, R pi plus IB multiplied by the equivalent resistance of R1 parallel R2 parallel R signal, because now this resistor R1 R2 is parallel with R signal. Both terminals are connected to each other. R1 parallel R2 parallel with R signal equal to 0. So either IB is equal to 0 or R pi plus R1 parallel R2 parallel R signal is equal to 0. Of course, that doesn't equal to 0 because R pi is not 0. R1 and R2 are not 0. R signal are not 0. So we have this only option that IB is equal to 0. So basically, this is open circuit. So if we look like this, if we look from these 2 points, we're going to look and find only RC. Okay. Now EV naught, number 3. And RC, of course, is known. So RC is 3.9 kilo ohms. AV naught. So for AV naught, it's VO over V input without V signal. So I'm going to have the circuit like this. RC, and there is no R load, beta IB. And let's do it in another way. So I showed you, this way that I'm gonna do right now. I showed you before how to do AV naught by removing RL, but we can do it another way. We can determine EV first, then we make the limit RL equal to infinity or estimated to infinity, limit to infinity, and then we can deduce EV naught from EV. So let's do that. So I'm gonna do, but of course, if you wanna do the first way, that's fine. So I'm gonna use the same circuit, exactly the same circuit, which is what we have here. So I'm gonna get AV, then AV naught. So AV is VO over V input, and everything is there. I mean, RL is there, our signal is there. Here is VI. So VO is, if this is beta IB, it's flowing in the equivalent resistance of RC and RL, the parallel equivalent between them. So it's so VO is equal to minus beta IB, RC parallel RL. Why? Because it's flowing from down to up. You can draw this here like this. It will be like this. RC parallel RL. So IB is flowing from bottom to up. How about VI? So VI is the voltage of R1 parallel R2, or the voltage of R pi as well, right? Because they are parallel. The voltage of R pi, we know it's IB R pi. So IB R pi. So IB will go with IB, we get it. So minus beta RC parallel RL over R pi. Okay, that's EV. Now let's get EV naught. EV naught can be represented as the limit when RL equal to, tends to infinity of EV. That's really nice because just remove RL and put infinity. So minus beta RC parallel with infinity over R pi. Parallel with infinity. What is parallel with infinity? If you have, a resistance like this in parallel with an infinite resistance. So the equivalent will be basically the same resistance. Let's call it R, RL, or whatever, RC here. RC. So that's basically minus beta RC over R pi. Okay. And remember, these are the same expressions that we get from, the first circuit that we explored. Exactly the same. I mean, the voltage divider circuit, in AC analysis become just like one resistance between the base and the ground. Finally, number 5, GV. Of course, guys, EV and EV naught, I'm showing you a new way to do it. But you can do in the same way that I'm just, pushing new ideas in your mind. If you want to do in the same way, the same sequence, EV nodes and EV, that's fine. You can do that. You have many ways to get EV and EV node. Okay, I teach you 3 ways now. The first way is to find EV from the circuit after removing RL. Then, EV node, remove RL and find VO over V input. Then add RL again, bring it back again, and find VO over V input when you add, after adding RL. This is one way. Another way is to find EV node from the circuit after removing RL, VO over V input. Then for EV, AV is equal to EV naught R load over R load plus R output, the output resistance of the circuit. This is another way. Here is a third way. In the third way, you will find EV first, then EV naught by taking the limit RL equal to infinity. Okay. A resistance equal to infinity, that means it's open circuit. That's it. Okay. JV is equal to AV, our input over our input plus our signal. Okay. So we know our input, we know our signal, and we didn't calculate V. So if we calculate, AV, so AV here is equal to, because we have the numbers, we have everything known, so let's do it. It's minus 97.67. So GV is equal to AV is known now, and our input and our signal are also known. So this will give us, minus 36.36. Okay. That's basically, guys, a complete, circuit analysis from the very start point in DC analysis to the last point, which is finding GV. Okay, guys, thank you very much for watching this video, and see you in the next video. Bye-bye.